The next thing we will talk about is the concept of a heterogeneous equilibrium, where there is more than one phase at equilibrium. Some reactants or products are in different phases from others. The first thing we'll look at are pure liquids and pure solids. If you think about it, pure liquids and pure solids have a fixed volume, and so they won't spread out to take up all the volume that they can access. As a result, let's think about this. This means that the concentration actually doesn't change, so it's effectively 1. And this fits in with the definition of activities, which some of you may see later in physical chemistry. But for our purposes, what we need to know is that as long as there's some pure solid or pure liquid reactants or products, pure solids and liquids do not appear in the equilibrium constant expression. So look at this reaction here. We can write the equilibrium constant in terms of concentrations in molarities as the concentration of carbon dioxide divided by the concentration of carbon monoxide squared. We can also write it in terms of partial pressures. In this case, it is the partial pressure of carbon dioxide divided by the partial pressure of carbon monoxide squared. Let's look at some more examples. Here, in the first one, we have aqueous solutions, so guess what? We are not going to write them out in terms of partial pressures. So Kc is equal to 1 over, using the 1 here because we don't include this pure solid, and we divide by the concentration of mercury 1 ions times the concentration of chloride ions squared. In the second case here, we'll write an expression for Kc, not Kp. Even though we have gases here, because we've got an aqueous phase substance here, we're going to write it in terms of concentrations at this point. There may be slight changes when we get to studying thermodynamics. So here, looking at the numerator, it is the concentration of sodium hydroxide times the concentration of hydrogen gas. Because neither of these have coefficients other than 1 here, we do not have powers that we raise these to. On the reactant side, we only have pure solids and liquids, so we don't see it. So this is the expression for Kc in this case.